Hello everyone, this is lecture 3, Solutions to Dynamical Systems. In the last two lectures, what we have done is we deal with difference equations. We approximate the solution of some using difference equations. So the drawback of difference equation is that different equation formula help you compute the next term given the immediately previous term in the sequence. However, it does not compute the value of a very specific term directly, right? And that is really a drawback because we don't want to actually calculate 10,000 terms before you want to know you can get the value of 10,000 in one term, right? So that's where it's coming here in lecture 3. We want to develop a solution or formula such that you can compute the value of a specific term directly, right? And we're going to look at two different models. The first one is the discrete exponential related to discrete exponential functions. And the second one is including the exponential functions and the constant functions. And we'll see that in a few minutes. So the learning objective is to build solution to some dynamical system. Again, dynamical system consists of two equations. The first one is the difference equations, and the second one is the initial conditions. Right? So let's quickly remind us what the dynamical system is. So it consists of two parts, right? So the an plus 1 minus an equal to f of a sub n and a0 value. Right? Depends on the problem, you have different value for the initial conditions. And we're going to learn how to examine dynamical system for which small change in the proportionality constant cause widely different predictions or not. Okay, so we'll see that later on in this lecture as well. All right, before we go into example, I'm going to write down a method. It's called the method of conjecture. So this is a very powerful mathematical method, powerful mathematical technique to hypothesize the form of a solutions to a dynamical system and then to accept or reject the hypothesis. Right, sometimes you propose a formula and sometimes it works, sometimes it does not work, but at least you can come up with some conjecture or some hypothesis for the form of the solutions to the dynamical system that you want to work with. All right, so let's start with the first example here. So this example is similar to, or at least the information is very similar to example 1 in lecture 1. So I want to quickly note that this is very similar to example 1 in lecture 1. All right, so if you have forgotten about this example, you can go back to lecture 1 and review that quickly. So the problem is that you have a saving certificate, right? Initially worth $1,000, accumulated interest pay each month at 1% of the balance. Again, this is not really realistic in real life situations because there's no bank will give you 1% for each month to accumulate the interest. All right. So no deposit or withdrawals occur in the account, and we can determine the dynamical system, right? And we got that a sub n plus 1 equal to 1.01 a sub n, and the initial amount of the saving certificate is $1,000. All right, so what we do is, let's say we want to compute a value of the certificate at some point in the future, right? And you don't want to actually just calculate the value of the account using these difference equations, right? You want to come up with the formula so that you can directly compute the amount at any given time in the future. All right, so we look for a pattern from this particular starting point. So we look for a pattern that we start with a sub 0 is going to be equal to $1,000, of course. And then A1 can be calculated as 1.01 times A0, or this is 1.01 times $1,000. So I'm gonna leave it like this, and I'm not gonna exactly calculate the value of this multiplication because I want to look for a parent here. Now A2 is equal to 1.01 times A1, and this is equal to 1.01 times 1.01 times $1,000. So if you notice, you have that this is 1.01 square times $1,000. Now for A3, is going to be 1.01 times A2, or 1.01 times 1.01 square times $1,000. And therefore you get 1.01 to the third power times $1,000. All right. Now you can continue with this process to actually give a predictions on the pattern of the sequence. But at this point, I can see there's a certain pattern here, right? We always have the initial amount here, which is $1,000 in each term in the sequence. And there is a number that raised to the power corresponding to the number in the sequence. So if you have A1, this number 1.01 get raised to the first power. For A2, the number get raised to the second power. For A3, the number get raised to the third power, right? So I recognize that parent, and I can give a conjecture. That A sub n is equal to 1.01 raised to the n power and multiply with $1,000, right? And I'm going to test the this conjecture, right? So I'm going to test the conjecture. Fine. So how could you test the conjecture? Just basically substitute what you know into this difference equation. So you have A sub n plus 1, which is 1.01 raised to the n plus 1 power times $1,000. That's for the left-hand side. The right-hand side is 1.01 times 1.01 raised to the n power times 1,000. And if you notice, this is the true statement because the left-hand side equal to the right-hand side. And you can conclude that this conjecture that you test, or the formula that you hypothesize, is working. It fits with the idea that it give the true statement when you substitute into the difference equations, and also when you substitute into the initial conditions, because you always start with the initial conditions of $1,000 in this particular case. Now you draw the conclusions that A sub n is equal to 1.01 raised to the power n times the initial value A0, where A0 is, of course, equal to $1,000. And n in this case is 0, 1, 2, 3, and so on and so forth. All right, so that is the procedure for us to obtain the formula for to calculate the value of this one particular value of the sequence given any value of n. Okay. And there are certain procedure for this method of the conjecture, right? So the first one is to look for the pattern, observe the pattern, hypothesize the form of the solutions to the dynamical system. That's what we did, right? And test the conjecture by substitutions. And then if it works, it gives you a true statement, then you can accept the hypothesis. If the conjecture doesn't work, then you reject the hypothesis and look for another form of the solutions. And then the last step is to attempt to discern a pattern to the solution based on explorations and observations. Okay, so let's continue with the next topic, right? So, which is linear dynamical system of the form a sub n plus 1 equal to r times a sub n, right? If you again noticed what we have done, this is a sub n plus 1, assume, is equal to r times, a sub n plus 1 equal to r times a sub n, right? And that is the linear dynamical system that we are dealing with, and we're going to come up with a more direct formula to calculate the value of the sequence. All right, so we say that the dynamical system in example 1 is of the form. So again, we look for a pattern. We just try to follow the procedure that we got up over here, right? So the first one is to observe the pattern. So look for a parent. And this is what you get, right? So a sub n plus 1 equal to r times a sub n. Right, so in example 1, r is equal to 1.01, but let's not care too much about that value at this point. And then you can start with a1 is equal to r a times a0, a2 is equal to r times a1, or you can replace a1 by r times a0, and you get r squared times a0. A3 is equal to r times a2, or you can replace a2 by r squared times a0. So this gives you r times r squared times a0, or this is r cubed times a0, right? And again, hopefully after this step, you can recognize the pattern and you can provide a conjecture. That a sub n is equal to r raised to the n power times a0 for n is equal to 0, 1, 2, 3, so on and so forth. And we're going to test the conjecture. By substitute this, right, this formula into the linear dynamical system of this form. And we get, so a sub n plus 1 is r to the power n plus 1 times a0 equal to the right hand side, which is r times r to the power n times a0. And the right hand side, if you rewrite the right hand side a little bit, you can see that this is also r raised to the n plus 1 times a0. So the left-hand side equal to the right-hand side is the true statement, and you accept the conjecture or the formula that you hypothesize, right? So because we accept the solutions, the formula of this linear dynamical system, I'm going to put this in a theorem. So the solution of the linear dynamical system a sub n plus 1 equal to r times a sub n for any non-zero constant r is given as, so a sub n equal to r raised to the n power times a sub 0, for a sub 0 is the initial conditions or initial value. Okay. All right, so this is discrete exponential functions, right? So we did this in lecture 2 as well. So we're going to use this to calculate some sewage treatment in the next example. Okay, so in this example, a sewage treatment plant processes raw sewage to produce usable fertilizer and clean water by removing all other contaminants. The process is such that each hour, 12% of the remaining contaminants in the processing tank are removed. Okay, so let's just try to summarize what we got in the given example so far, right? Without looking at the question just yet, right? So a sub 0 is the initial amount of sewage contaminant, and a sub n is the amount of sewage contaminant after n hours. All right, and you have the reduction rate is about a 12% or 0.12. So after so for each hour, 12% of the remaining contaminant is in the processing tank are removed. Okay, so you need to come up with the let's say you want to come up with the linear dynamical system, just like we did in the last two lecture. The model can be that of a sub n plus 1 minus a sub n to indicate the difference equations equal to, so because you want to remove the contaminants, so we're going to have the negative 0.12 a sub n, or you can solve for a sub n plus 1. That is going to be 0.88 a sub n. Okay, so this is the linear dynamical system, right? And you can connect this linear dynamical system with the solutions that we just obtained in this theorem, right? So for R is the reduction rate in this case. So instead of using these difference equations, we can relate the different equations to the discrete exponential growth or exponential functions. Or you can, so let me quickly note that this is the linear dynamical system. And you can relate this back to the discrete exponential functions. And a sub n is equal to 0.8a. Let me be careful here. So r to the power n times a0, or r to the r is 0.88 raised to the power n times a0. And we can do that from theorem 1 that we just built up in the previous page. Okay. Okay, now we have the formula for the model. We go to the questions. What percentage of the sewage could remain after 1 day? Okay, so after 1 day, it's going to be 24 hours because everything is done in the with the time in hour. Okay, so part A, so after 1 day or 24 hours, you have a sub 24 is going to be equal to 0.8a raised to the power n, in this case 24, times the original value, which is right, it's not explicitly given to you, so that's why we keep it at A0. Right. And the quick calculations will give you this 0.88 raised to 24th. It's going to be 0.046580. So after 24 hours, the amount of sewage contaminant is about 0.0465 times A0. And you can draw conclusions that the level of contaminant in the sewage has been reduced by more than 95% at the end of the first day. Right. And you may wonder where's 95% coming from. Is actually coming from this particular number, right? So after 24 hours, the amount left in the tank is just about 0.0465 of the original amount of contaminant. And you can come up or calculate the 95% because you take 1 minus 0.0465 and give you 0.9535. So it's approximate. It's going to be about 95%, right? Or more. Right, let me be more precise here. 95.35%. Okay. So after one day, 95, more than 95% of the contaminants get removed from the tank. Okay. Now part B. So part B tells you, asks you to calculate how long would it take to lower the amount of sewage by half. So they're looking for the value of n, right? The number of hours, such that if the original contaminant remained. Well, all right, in the tank. So I don't know the exact value of n, but I know that after a certain n hours, a sub n is going to be equal to 0.5 a sub 0, right? So therefore, you can substitute this, right? And set this equal to 0.8 a raised to the n power times a sub 0, right? So you substitute this into the model that we come up with, right? And then you can cancel a sub 0 on both sides of the equations. And to find the value of n, what you do is you take ln on both sides of the equations. Should be a very straightforward calculations. And n is going to be equal to ln of 0.5 divided by ln of 0.88, and is approximated at about a little bit more than 5 hours. Now for part C, they ask you to calculate how long until the level of sewage is down to 10% of the original level. So it's, we look for n such that a sub n is going to be also 10% of the original contaminant remain in the tank. That means 90% of the contaminant get removed from the tank, right? So after a certain n, you have a sub n equal to 0.1 A0, and you set this up to be equal to 0.88 raised to the power n times a0 again. You cancel out a0 on both sides of the equations, and then take ln on both sides, and you get, or n is equal to ln of 0.1 divided by ln of 0.88, and is approximately equal to 18.01 hours. Right, you can draw a conclusion that it takes about 18 hours before the contaminants are reduced to 10% of the original level. Okay, so hopefully this gives you some idea how to use how to turn the linear, how to turn the given information into a linear dynamical system, and then also come up with the formula related to discrete exponential functions. And in this case, it is exponential decay because everything will decay over time. And that's it, right? So that's it for for this example. I'm gonna move on to the long-term behavior of this linear dynamical system of the form a sub n plus 1 equal to r times a sub n. Right. So there are multiple cases that you need to focus on. The first one is where the rate or r is equal to 0. That means all values of the sequence is going to be 0, but except maybe possibly at the initial data, right? Except possibly at a0. Right? All the values of the sequence are zeros, except possibly at a0. Okay. When r is equal to 1, then you have a sub n plus 1 equal to a sub n. So that is the value of the sequence remain the same regardless of the initial conditions, right? So if the initial condition is equal to 1, a1 is equal to 1, a2 also equal to 1, so on and so forth, right? So you have a constant sequence, right? When r is greater than 1, then you have a sub n equal to r raised to the n power times a0. This sequence will increase without bound. When r is less than -1, then you have that the sequence a sub n equal to -1 raised to the r raised to the power n times a0. This becomes alternative sequence, right? It's going to move between positive and negative value, and therefore the value will oscillate. Now, when absolute value of r is between -1 and 1, then you have a sub n equal to, again, r raised to the power n times a sub 0, right? The value will decay to the limiting value of 0. Right? So this is exponential decay. This is exponential growth. Okay, so you have a multiple graph here to indicate the long-term behavior of the sequence or of the discrete exponential functions, right? So for the first graph, this increases without bound. And this is the case when R is greater than 1 and A0 is a positive number, right? And for this graph, this is actually also increases, but on the negative side, right? So increases without bound on negative. This is the case for, again, R greater than 0, but the initial condition is a negative number. This graph is exponential decay, right? So decayed to 0 when you have R is between 0 and 1, and A is greater than 0. Right. If you have the A0 is greater than 0, so you have the initial condition started on the positive side of Y. Now this is going to decay to 0 as well, but the value of A0 is in the negative sign, right? So R is between 0 and 1, and A0 is less than 0 as well. The next two cases is for the case of oscillations. This is where R is less than -1 and will grow, oscillated and grows. Let me be careful here. So oscillates and grows. This is the case where R is less than -1 and A0 is greater than 0, right? And this is oscillate and decayed, right? Decays to 0 when R is between 0 and -1, and A0 is also a positive value, right? So these are the cases for the long-term behavior of the discrete exponential growth, right? So it depends on the value of R and the starting initial value as well. All right, so now the next linear dynamical system we want to look at is the one where we combine the term R sub A, R times A sub n, and the constant term B. So most of the time, right, so we get the linear dynamical system A sub n plus 1 equal to R sub R times A sub n plus B. So let me be careful here, sorry. So the change is proportional to A sub n, right? So that is delta A sub n equal to A sub n plus 1 minus A sub n. So that's how you come up with the difference equations. This is equal to R times A sub n because this is proportional to A sub n, right? And that's how we get the value of A sub n plus 1 equal to 1 plus R times A sub n. And that is the linear dynamical system in the last case that we're dealing with, even though we have 1 plus R, it doesn't really matter, right? Because we can substitute 1 plus r for another letter, and that is also the rates or the proportionality. Okay, in the case, or if the change is not proportional, but constant, what's going to happen? Then what we have is delta a sub n equal to a sub n plus 1 minus a sub n equal to some constant b, right? So in this case, b is some arbitrary constant, right? Then you can solve for a sub n plus 1 as a sub n plus b this is called the constant growth model. Or another name for this particular sequence is the arithmetic sequence. All right. And in general, we can combine both exponential growth and the constant growth models to obtain the following sequence. So in general, we combine both exponential growth or decay and constant growth models or decay, right, model to obtain a sub n plus 1 equal to r times a sub n plus b. And we note that this part of the equations is called the exponential growth or decay. And this part right here is the constant growth or decay. All right. And now we have the linear dynamical system, right? So a sub n plus 1 equal to r times a sub n plus b, given the initial condition is still a sub 0. Now you give a conjecture, right? You want to come up with a formula such that you can calculate any value of the sequence given any specific n, right? So you need to come up with, or you can hypothesize a formula for this particular linear dynamical system. So you look for a pattern, right? So look for a pattern. So that is, you start with A1, this is equal to R times A0 plus B, and A2 is equal to R times A1 plus B. And then you can substitute A1 as this, with this expression. You get R times R, A0 plus B, or this is equal to r squared times a0 plus r plus 1 times b. And a3 is r times a2 plus b. Then you can substitute a2 by this formula. You get r times r squared a0 plus r plus 1 times b. And if you distribute r, you get r cubed a0 plus r squared plus r plus 1 times b. I forgot this b here, so move this down here, get add with another b. Okay, so hopefully we recognize the pattern here. If you continue work out the come up with the pattern for the sequence, you will see that conjecture that a sub n has the form r raised to the power n times a0 plus r raised to the n minus 1 plus r raised to the n minus 2, so on and so forth, plus r squared plus r plus 1 times b. And this is the formula I want to propose, right? However, this is a little bit complicated, right? Because you have a bunch of polynomial functions, right? A bunch of terms here, just the polynomial functions. So what I do is I'm going to reduce the complications of the model or of the formula by propose that. So it can be shown that 1 minus r raised to the power n is equal to 1 minus r times 1 plus r squared, so on and so forth, up to r raised to the n minus 1. And you get that this particular formula using the long divisions, right? So if you take 1 minus r to the power n divided by 1 minus r, you will get this polynomial functions. Okay, so we can rewrite 1 plus r squared plus r raised to the n minus 1 as 1 minus r to the power n divided by 1 minus r. Right? And we're going to substitute these fractions into our hypothesis. Okay, let me add another page here. Okay, so the formula we want to propose now becomes, that a sub n equal to r raised to the power n times a0 plus 1 minus r raised to the power n divided by 1 minus r times the value of b. And we want to know if this actually works for our model linear dynamical system of this form. We go and substitute our formula into this linear dynamical system, and hopefully you get the true statement, right? So the next thing is to test for the conjecture, or test the conjecture. Right. So a sub n plus 1 is going to be r raised to the n plus 1 times a0 plus 1 minus r raised to the n plus 1 divided by 1 minus r times b, which is equal to r times r to the power n times a0 plus 1 minus r raised to the power n divided by 1 minus r times b. And we got r raised to the n plus 1 times a0 plus, this is r times 1 minus r to the power n divided by 1 minus r times b. So I forgot the plus b in the right hand side. So the plus b here. Okay. So I'm gonna combine these two terms by finding the least common denominator. So let me work out the details here. R raised to the n plus 1, a0 plus r times 1 minus r to the power n times b plus b times 1 minus r divided by 1 minus r. And if you distribute the value of b, you get rb minus r raised to the n plus 1b plus b minus br divided by 1 minus r. And you can cancel out these two terms. And you, again, on the numerator, take b as the common factor. You will get r raised to the n plus 1 times a0 plus 1 minus r raised to the n plus 1 divided by 1 minus r times b. So the left hand side equal to the right hand side is the true statement, and we're going to accept our conjecture that this is the formula to calculate the exact value of any number in the sequence given any specific value of n. Okay. And this is the formula is for this particular sequence right here. Okay. So we good with that. All right, so that's the formula. Now in the next example, I'm gonna relate the formula which is come up with this particular example. Okay, so in this example, we talk about digoxin is used in the treatment of heart disease. So doctor must prescribe an amount of medicine that keeps the concentration of digoxin in the bloodstream above an effective level without exceeding a safe level. There is variations among patients for an initial dosage of 0.5 milligrams in the bloodstream. So let's summarize what we got so far. We say that n is going to be a number of days. A sub n is the amount of digoxin remaining in the bloodstream. And this is the number of days. This is the amount of digoxin remaining in the bloodstream after each day. And this is the change that get calculated from the given table, right? And so what we do, okay. So what we're gonna do is very similar to lecture 2. We're gonna build a model for different equations, and this models will relate to the exponential decay or exponential growth, depends on the rates that we're going to get. So in the first column is the number of days. The second column is the amount of the drug in the bloodstream. And this column is the difference. So, or the change of the amount of drug in the system in the bloodstream. Okay, so I'm gonna plot these two data together. So we select these two columns, click insert, select this scatter plot, and you have this point. Click on this any point on the plot and hit right click, add trend line, and you choose linear approximations and display the equation on the chart. And we're going to choose negative 0.31 as the answer, right? So that's the proportionality constant that we look for, okay, for the difference equations. Now let me go back to the notes. So we just estimate that. So by estimations, the constant coefficients is negative 0.31. Then the difference equation is a sub n plus 1 minus a sub n equal to negative 0.31 a sub n, or a sub n plus 1 is equal to 0.69 a sub n, right? And a0, of course, is equal to 0.5, which is the initial value. And this is the linear dynamical system. right, of the form a sub n plus 1 equal to r times a sub n. And because of this linear dynamical system, you can write the formula to help calculate any value of a sub n given any value of n. So then you have that a sub n is equal to negative 0.31 raised to the n power times a sub 0. Okay, so now another method that we want to impose to this example is that suppose we prescribe a daily drug dosage of 0.1 milligrams and know that half of the vaccine remains in the system at the end of its dosage period. All right, so suppose we prescribe a daily drug dosage of 0.1 milligrams and know that half of the drug remains in the system at the end of each dosage period. Okay, so you have a sub n plus 1 equal to 0.5 times a sub n, right? Because after each dosage, 50% or half of the drug remain in the system. But you have an additional component or additional information for this particular problem is that you add 0.1 milligram of drug dosage into the system every after each dosage period. That means you have a constant growth of 0.1. Okay, so this is the, again, you still have A0 equal to 0.5, which is the initial amount. And this is the linear dynamical system. Of the form a sub n plus 1 equal to r times a sub n plus b. Okay, and depends on the value of the initial value, right? You can actually have a different performance on the amount of drugs, right? But overall, what you see is that it's always come out to be about 0.2, as you can see in this graph, right? So there are three cases that you want to look into. The first one is the amount of 0.1. The second one is the amount of 0.2. And the third situation is the amount of 0.3. And for each case, all the amount of drug will decay to 0.2 if given a different initial value. Right? So given a sub 0 equal to 0.1, a sub 0 equal to 0.2, and a sub 0 equal to 0.3, you have different calculations, but it's always come down to be 0.2. Okay. So that's it for me for this particular lecture. So in this lecture, we look at the solution for dynamical system, right? So again, dynamical system consists of two parts. The first one is the dynamical, the difference equation, and the second part is the initial value. We learned about method of conjecture, and there are certain procedures that you can follow. And the first one is to look for a pattern, provide the conjecture and test the conjecture, and then draw the conclusions. Okay. And the example given in this lecture relate back to the discrete exponential growth and the combination of exponential growth or exponential functions and constant functions. So that's it for me. Please let me know if you have any questions. Thank you.